This video will show how to locate and identify maximum and minimum values of a function from its derivative. Let's start with a few definitions. Let f be a function with domain D. Then f has an absolute maximum value on D at a point C if f of x is less than or equal to f of c for all x in D, and an absolute minimum value on D at C if f of x is greater than or equal to f of c for all x in D. In this lesson, maximum and minimum values are also referred to as extreme values. It is important to define our domain D when we refer functions. Here's why. In the function rule, y equals x squared, the absolute minimum and maximum values vary depending on the defined domain. If we look at the natural domain of the function, negative infinity to infinity, there will be no absolute maximum and the absolute minimum of 0 at x equals 0. If the domain is reduced to the inclusive domain of 0 to 2, there will be an absolute maximum of 4 at x equals 2 and an absolute minimum of 0 at x equals 0. However, even a single point of discontinuity can keep a function from having either a maximum or minimum value on a closed interval. If we look at the same function y equals x squared, but with a domain of non-inclusive 0 to inclusive 2, the absolute maximum remains 4 at x equals 2. However, there is no absolute minimum, since the minimum of 0 is not included in the set. Similarly, if the domain was non-inclusive on both ends of this domain, there will be no absolute extreme at all, since they are not included in the domain. This example leads us to our first theorem, the extreme value theorem. If f is continuous on a closed interval a, b, then f attains both an absolute maximum value, capital M, and absolute minimum value, lowercase m, in inclusive a, b. That is, there are numbers x1 and x2 in the closed interval a, b, with f of x1 equals the absolute minimum, f of x2 equals the absolute maximum, and the absolute minimum is less than or equal to f of x, which is less than or equal to the absolute maximum for every other x in a, b. This theorem shows us that for any closed interval on a continuous function, there will be an absolute maximum value capital M and an absolute minimum value lowercase m. As you can see in this example, the function cosine of x, in the domain that is pictured here, we can see that the absolute maximum, capital M, is 1 and occurs at x equals 0 such that f of 0 is equal to 1, and the absolute minimum, lowercase m, is negative 1 and occurs at x equals pi such that f of pi equals negative 1. Now what happens if the domain gives us a minimum value that is not absolute, or a maximum value that is not the highest? We have two more definitions for these cases. A function f has a local maximum value at a point C within its domain D if f of x is less than or equal to f of c for all x in D lying in some open interval containing C. A function f has a local minimum value at a point C within its domain D if f of x is greater than or equal to f of c for all x in D lying in some open interval containing C. Looking at this function on an inclusive domain of 0 to 3, the absolute maximum value is located at x equals 3, and the absolute minimum value is located at x equals 0. However, there exists a local maximum point C1 at x equals 1, where there is no greater value of f nearby. Also, there exists a local minimum point C2 at x equals 2, where there is no smaller value of f nearby. The next theorem explains why we usually need to investigate only a few values to find a function's extrema. The first derivative theorem for local extreme values if f has a local maximum or minimum value at an interior point C of its domain, and if f prime is defined at C, then f prime of C equals 0. This theorem says that a function's first derivative is always 0 at an interior point where the function has a local extreme value, and the derivative is defined. If we recall that all the domains we consider are intervals or unions of separate intervals, the only places where a function f can possibly have an extreme value, local or global, are the following. 1. Interior points where f prime equals 0. This can be located visually when the graph changes from positive to negative slope, or vice versa. 2. Interior points where f prime is undefined. This can be located visually when the graph has a maximum or minimum but not a derivative of 0, or a spike in change in slope. We are going to call these first two types of points critical points. 3. Endpoints of the domain of f are another place where extreme values can exist on a function. Let's look at a few practice examples to find the absolute extrema of a continuous function f on a finite closed interval. We will use the following two steps to find the absolute extrema of continuous functions f on finite closed intervals. 1. Evaluate f at all critical points and endpoints. 2. Take the largest and smallest of these values. Question 1. Find the absolute maximum and minimum values of the following function on the interval -2, 1. Visually, on the graph of y equals x squared, you can see where the minimum point is located between the domain of x equals -2 and x equals 1. In this case, the minimum point appears to be at the origin, with the absolute maximum occurring when x equals -2. Let's verify this. If we evaluate our function at the endpoints, f of -2 equals -2 squared equals 4. F of 1 is equal to 1 squared equals 1. To find our critical point, we differentiate the function using the power rule. We get f prime of x equals 2 times x. To verify the critical points, we set the derivative to 0. So f prime of 0 is equal to 2 times 0 is equal to 0. Therefore, the function has an absolute maximum value of 4 at x equals -2 and an absolute minimum value of 0 at x equals 0, as those are the highest and lowest evaluated values respectively. Question 2. Find the absolute maximum and minimum values of f of x equals 10 times x times 2 minus the natural log of x on the interval 1 e squared. On this graph, it is more difficult to definitively say where the maximum lies. Let's follow the steps to ensure where our endpoints and critical points are to reveal the absolute extremas. If we evaluate the function at the endpoints, f of 1 is equal to 10 times 1 times 2 minus the natural log of 1 equals 20. And f of e squared equals 10 times e squared times 2 minus the natural log of e squared equals 10 times e squared times 2 minus 2 times the natural log of e equals 0. To verify the critical points, we find the derivative of the function. Using the product rule, we get f prime of x equals 10 times 2 minus the natural log of x minus 10 times x times 1 over x equals 10 times 1 minus the natural log of x. Evaluating at 0, we get 0 is equal to 10 times 1 minus the natural log of x. 0 is equal to 1 minus the natural log of x. 1 equals the natural log of x. So x equals e. So the only critical point in the domain is x equals e, where the natural log of x equals 1. Evaluating the function at this critical point, we see that f of e equals 10 times e. Therefore, the function's absolute maximum value is 10 times e, approximately 27.2, occurring at x equals e. The absolute minimum value is 0, and occurs at the right endpoint x equals e squared. In this last example, we will see how a vertex will differ from a curved maximum or minimum point. Question 3. Find the absolute maximum and minimum values of f of x equals x to the power of 2/3 on the interval -2, 3. Let's continue with our steps. If we evaluate the function at the endpoints, and at 0 we get f of -2 equals the cube root of 4, f of 3 equals the cube root of 9, and f of 0 is equal to 0. Let's take the first derivative of the function. F prime of x equals 2/3 x to the -1/3 power equals 2 over 3 times the cube root of x. As you can see, the evaluation of the first derivative at f prime of 0 will be undefined. Therefore, for the function on the given domain, the absolute maximum value is the cube root of 9, approximately 2.08, when x equals 3. And taking the smallest evaluated number, the absolute minimum value is 0 when x equals 0. Thank you for watching our video on the extreme value theorem and the first derivative theorem for local extreme values. Be sure to like, subscribe, and leave a comment below. Thank you.